Right, continuing on our theme of circles, when we draw two chords on the interior of a circle, each chord is divided into two segments called the segments of the chord. So here we have chords A, B, and C, D, and they cross at point E, and they're separated into EA, EB, ED, and EC. And this is important to us because when two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord, which means that EA times EB, EA times EB is equal to purple ED times EC, ED times DC. So let's look at an example. Here we have two chords, ML and JK, that intersect, and we want to find the length of the segments ML and JK. So we know that the length of ML is going to equal x plus 2, this segment, plus x plus 1, this segment, and JK is going to equal x plus 4. This segment plus this segment gives us the distance of both chords. But we don't know what x is, so we can use our theorem to figure what it is. And our theorem tells us that x times x plus 4 is going to equal x plus 2 times x plus 1. So now we just have to go through and solve for x. Well, here we have 2x plus 2 times x plus 1. We use FOIL for that, so we do first x times x is x squared, plus outside x times 1 is x, inside 2 times x is 2x, and then last 2 times 1 is 2. And then for x times x plus 4, we just distribute the x. So x squared plus 4x. And that's going to come down here. And before we go any further here, we have to simplify, combine like terms. So x squared is x squared. X plus 2x is 3x. And then 2 is still just 2. So let's get into our algebra and see if we can't get x by itself. Let's subtract x squared from both sides. That'll cancel and that'll cancel, leaving us with 3x plus 2 equals 4x. We can subtract 3x from both sides and end up with x equals 2. So now that we know what x equals, we can come back here and plug it into our formula. And so if x equals 2, I'll just substitute 2 for x. So ML equals 7. Let's do the same for JK. And JK equals 8. And we are done with that one. Let's look at one more. So again, we want to find the lengths of RT and SU. RT is going to equal x plus 1 plus 3x, and SU is going to equal x plus 4x. But to solve for x, we're going to have to use our theorem and multiply our factors to figure it out. So x times 4x equals x plus 1 times 3x. So we end up with 3x squared plus 3x equals 4x squared. We can subtract 3x squared from both sides. That cancels. That leaves us with 3x equals x squared. So now we can divide through by x and get x equals 3. And now that we know that x equals 3, we come back up here and plug it in to our original formula. 3 plus 4 times 3. 4 times 3 is 12 plus 3. SU equals 15. Come over here and we have 3 plus 1 plus 3 times 3. 3 times 3 is 9. 3 plus 1 is 4. So RT equals 13. And we